Hello everyone, I hope you are all doing well. Please, can you confirm if you can hear me? Okay, it seems like... Okay, I can see myself, so everything is fine. Guys, there was a lot of miscoordination for this stream, and I truly apologize for that. I will write a text in Telegram and explain what was going on. Let me also announce that the stream has started. Today we're gonna talk about number theory. I'm sure that it is gonna be super helpful. I mean, I've prepared so many good topics to talk about, and I really hope that it can help you a lot. So, salam. Thank you very much. And hello to other guys. So, I hope that you will learn a lot from this topic stream, and if you are ready, without any further ado, let's get started, shall we? How to become a poet. Nice. Okay, so let's get started. And let me thank you very much for joining and for your patience because of all the issues that happened. So we're gonna start today. We're gonna start from simple topics, and we're gonna move up to more complex topics gradually. And we try to cover all the important topics that you are going to need in number theory. So let's get started with the first thing that I want to say today. Guys, in number theory, there are several topics that have very high importance. One of the most important things that in number theory you see in many different problems is GCD. So you have to know that what GCD is and know how to calculate it. I mean, you have to make some intuitive foundation about GCD to completely understand that what is going on there. That's gonna help you a lot to have a better concept of number theory. So this is the first thing that we're gonna talk about today. First of all, and then we're gonna solve some CF problems with this topic and see that how often you see it in Codeforces problems and in the problems in competitive programming. First of all, what is the definition of GCD? Can you help me with that? I think no topic is by itself enough. I mean, you have to make a foundation about many topics and especially solve so many problems. What it makes you pupil is solving so many problems and learn from. Thank you very much, Anshu. Yes, exactly. So GCD is greatest common divisor. So it means that it is the greatest number that divides several numbers. Most of times to GCD we give only two numbers, but you can also give it more than two numbers. I mean, to GCD function you can give n numbers as well, and the answer is gonna be the greatest number that divides all these numbers. I mean, all these numbers are a multiple of that number. So in particular, as I said, most of times we use two numbers in GCD. For example, we say GCD of A and B, but as I said, we can also give this function more than two numbers. So if GCD of A and B is equal to D, it means that A is divisible by D and B is divisible by D and D is the greatest number with this properties. D is the greatest possible such number. For example, GCD of 24 and 16 is 8. You know, if you see all the common divisors of 24 and 16, you see that also 2 is a common divisor. Also 4 is a common divisor. Also 1 is a common divisor. And 8 is a common divisor. Among them, 8 is the greatest one. So the greatest common divisor is 8. So far, I know that most of you knew the definition of GCD. So now we get to where things get more interesting. So this is the definition of GCD, the greatest number that two numbers or more numbers all divide that number. All of them are divisible by that number. Now, let's say I want to say a very important fact about GCD. A fact that is so much importance. I want to prove that GCD of A and B, assuming that A is greater than B. Without loss of generality, we can assume that A is greater than B. A is greater than or equal to B. I mean, either A is greater than or equal to B, or B is greater than or equal to A. Okay, or both, if they are equal, both of them. So one of them is greater than or equal to the other one. I want to prove that GCD of A and B is equal to GCD of A minus B and B. This is one of the most important facts about GCD. So we want to prove that GCD of A and B is equal to GCD of A minus B and B. And first, let me tell you something. What is GCD of x and 0 for any x greater than 0? What do you think GCD of x and 0 is? Because I'm saying it because when A is equal to B, by definition, I mean when A is equal to B, I'm saying that GCD of A and B is equal to GCD of 0 and B. What is GCD of x and 0? Exactly, GCD of x and 0 is gonna be equal to x. Because 0 is divisible by everything. I mean, 0 is the best number. I mean, you can divide 0 by everything. 0 is the multiple of every integer. So it's like any number that you choose, 0 is a multiple of that. Because 0 times that number is 0. So it's going to be equal to the other number. Because for the other number, the greatest divisor of x is x itself. And for 0, every number is okay. 0 is like something that everything is okay with me. So you can, everything you choose, I'm a multiple of that. So GCD of x and 0 is going to be equal to x. Because for x, the greatest possible divisor is x. For 0, everything is okay. So GCD of x and 0 is x. So this is correct even when A and B are equal. When A and B are equal, the GCD is equal to them. GCD is equal to A when both of them are A. And it's equal to GCD of 0 and A or B. So when they are equal, this is correct as well. So now I want to prove that. I want to prove that this is correct. So how can I prove this? Let's prove this by contradiction. Assume that this is not correct. I easily show that it's not possible that it's correct. And you will see that. You will get a grasp of why they must be correct. They must be equal. So assume that, for example, GCD of A and B, there are two cases. Either GCD of A and B is greater than GCD of A minus B and B, or GCD of A minus B and B is greater than GCD of A and B. So GCD of A and B is less than GCD of A minus B and B. So I want to show that both cases are not possible. So let's first prove these parts. Okay. So first I will prove that this is not possible. How do I say that? I say that if GCD of, you can't see this, GCD of A and B is greater than GCD of, let me make this a bit smaller. Okay, let's continue. If GCD of A and B is greater than GCD of A minus B and B, it means that there's some D, GCD of A and B is equal to some D. I want to show that it's not possible that GCD of A minus B and B is less than D. GCD of A minus B and B is also at least D as well. Why? Because I'm saying that if GCD is D, it means that A is a multiple of D. A is equal to some X times D. X is an integer, and B is equal to some Y times D. Y is also an integer. So when GCD of A and B is equal to D, it means that both A is a multiple of D and B is a multiple of D, right? As a result, A minus B is also a multiple of D, because A minus B is going to be X times D minus Y times D. It's going to be equal to X minus Y times D. And X minus Y is also an integer. This is also an integer. Therefore, A minus B and B also, both of them are divisible by D. So GCD of A minus B and B cannot be less than D, cannot be less than GCD of A and B. So this is a contradiction. Because we are saying that GCD of A and B is greater than GCD of A minus B and B, but we showed that GCD of A minus B and B is at least D. So it's like we are saying that D is greater than D. This is a contradiction. So this case is not possible. Is it completely clear? If you understood it well, please either put a plus in the chat or use this 100 emoji. So I just proved that if GCD of A and B is at least some D, GCD of A minus B and B is also at least that value D as well. Nice, great, nice. So let's now move on to the other part of it. Let's now prove that GCD of A and B is cannot be less than GCD of A minus B and B. Let's show that this is not possible as well. So far we showed that this case is not possible. Now if we show that this other case is not possible as well, we're done. So now we want to show that GCD, as we are assuming that GCD of A and B is less than GCD of A minus B and B. It is very similar. Very similarly, we show that it is not possible as well. Again, assume that this is equal to D. This is equal to some D. It means that B is a multiple of D. Okay, assume that it means that, for example, B is equal to X times D again. Also, A minus B is a multiple of D. Assume that A minus B is equal to Y times D. Both of them are multiples of D. Some integer times D. Now I'm showing that then I can say that A is going to be equal to A minus B plus B. The sum of these two values is equal to a. Is a minus b plus b. So I can say that it is equal to x plus y times z. A plus y is an integer. So it means that a is a multiple. A is a multiple of d. So in here, a is a multiple of d, b is also a multiple of d. Therefore, GCD of a and b is also at least d. Because we know that d is a common divisor. Maybe there is a greater common divisor as well, but d is a common divisor. So again, it showed that this is equal to d. This is at least d, but this is less than this. This is a contradiction. So this case is not possible as well. Okay, so this is also a contradiction and it is not possible. Is this part also clear? If it is, please again use this emoji or put a plus in the chat. And if it is not, let me know to go over it again. Nice, great. Thank you very much. Okay. So we showed that both of these parts are not possible. Let's make it bigger. Both of these parts are not possible. So we got a contradiction in both parts. So I proved that GCD of, I proved a very important fact, GCD of A and B is equal to GCD of A minus B and B, assuming that A is greater than B. Okay, if B is greater than A, I subtract A from B. I go in the other direction. So, this is correct. Now I'm going to use it to calculate GCD. Assume that we want to calculate GCD of two numbers. In what time complexity? I mean, we can calculate GCD of A and B. Assume that we want to provide an algorithm to calculate GCD of A and B. Well, the first algorithm that comes to mind is to have a for I from 1, for example, let's write in C++ format, I less than equal to. For example, I can go to minimum of A and B because I know that the greatest common divisor is at most A and it is at most B. So it's at most minimum of A and B. I plus plus, I can have this for, and I can just say that if A modulo I was 0 and B modulo I was 0, I can say that my GCD, let's define some int of ans that is 0 initially. I set my ans to be I because I can both say that ans is equal to maximum of ans and I because I find another answer, but I can also say that ans is equal to I because I is going forward. I starts from 1 and goes to minimum of A and B. So this I that divides both of the numbers is the maximum I so far. So I can say that ans is equal to I. So this way I can calculate GCD. And if I do this, my time complexity will be of minimum of A and B. It can work for small numbers, but as A and B grow large, I mean, for example, if A and B are at most 10 to the power of 9, if they can be up to 10 to the power of 9. If they will be up to 10 to the power of 6, if we have we have guaranteed that a and b are both up to 10 to the power of 6, this can work. If we just once we want to find the GCD of two numbers up to 10 to the power of 6. But if a and b are, for example, up to 10 to the power of 9 or 10 to the power of 18, this cannot work. This won't work. So far we have an algorithm to find GCD of two numbers in of minimum of a and b. But how can we make it better? How can we make it better than this? So in order to make it better, I'm going to tell you the next fact that's going to help us a lot. In general, in order to make it better, we're going to use the fact that we discussed right now. GCD of a and b is equal to GCD of a minus b and b. And now assume that, for example, we want to find GCD of, for example, 10 and 3. By the fact that we said GCD of 10 and 3 is going to be equal to GCD of 7 and 3. Because we said that GCD of a and b is equal to GCD of a minus b and b. But the point is, we don't need to stop here. We can apply it again. GCD of 7 and 3 again is equal to GCD of 4 and 3. But again, we don't need to stop here. We can apply it once again. GCD of 4 and 3 is going to be equal to GCD of 1 and 3. Or we can rearrange this and say GCD of 3 and 1. Okay, so if you see, we can apply it many times. I mean, as long as a is greater than or equal to b, we can say that a minus equal to b. So it's like when we get, we can define a function int of GCD, int a, int b, and I can say that as long as a is greater than or equal to b, while a is greater than or equal to b, a minus equal to b. Can you say that? What does it mean? What is the number that we get to at the end? When we say that while a is greater than or equal to b, a minus equal to b, what does it mean? At the end, what is the last number that I get to? What is the result here? What is the result here? Exactly. So as is seen here, exactly, it's a modulo b. So if we try to apply it again and again, it means that at the end we get to a modulo b. So not only GCD of a and b is equal to GCD of a minus b and b, assuming that a is greater than or equal to b, but also if we apply it over and over again, we can say that GCD of a and b is going to be equal to GCD of a modulo b and b. I'm sorry. Thank you very much for telling me. So let me go over it again. I'm saying that not only GCD of a and b is equal to GCD of a minus b and b, but also if we apply it over and over again, GCD of a and b is going to be equal to GCD of a modulo b and b. So we keep subtracting b from a, at the end we get to a modulo b and b. So we can always say that GCD of a and b is equal to GCD of a modulo b and b. And the point is that if you see, we don't even need to assume that a is greater than or equal to b. Even if a is less than b, it works. Because a modulo b, if a is less than b, a modulo b is equal to a. if A is less than B, A modulo B is going to be equal to A. So we're just saying that GCD of A and B is equal to GCD of A and B. Okay. So it works for any case, if A is greater than or equal to B, or A is less than B. So we can say that, and yes, another point is that A modulo B is definitely less than B. So next time B is gonna be our greatest number among these two. Between these two, B is gonna be the greater number next time. So now we know that when we have A and B, we can say that it is equal to GCD of A modulo B and B. So what we can say is that when we have GCD, when we want to calculate GCD of A and B, we can try to make our numbers smaller. When we have A and B, we can just say that, okay, turn it to GCD of A modulo B and B, or B and A modulo B, because I try to make the first number the bigger one. Maybe in the first step it's not, but from the second step forward, always the first number is going to be the greater number. So the point is that we know that now B is the greater number. It's equal to GCD of B and A modulo B. And maybe we can continue this process over and over again. And now the question is, if we continue this process over and over again, how many steps we're going to have in order to calculate GCD of A and B. We want to make A and B as small as possible. This is the general idea. We want to make A and B as small as possible so that we can easily calculate the GCD. So that we do not need to deal with great numbers, with very great numbers. We want to make them as small as possible so that we can easily answer the questions. Say that what is their GCD. When they are small, it's easy for us to calculate. So now we know this. We know that this is equal to GCD of A and B is equal to GCD of B and A modulo B. Now again, we need one more tool in order to find GCD with a better time complexity. And that other tool is another fact that is also very important in number theory. And that's it. Assume that we have two numbers, A and B, and A is greater than or equal to B. What I want to show is this. I want to show that A modulo B is less than A half. So this is also a very important fact in number theory. Generally it's saying that if you have two numbers, A and B, when you calculate A modulo B, A will be reduced at least by half. A will lose at least half of itself. So when you have two numbers, A and B, when you calculate A modulo B, A will be reduced at least by half. A will lose at least half of it. It is very important because it shows that, intuitively you can say that it shows that in here, by doing this, either if A is greater than or equal to B, in the first step we are not sure that A is greater than or equal to B, but the good point is that from the second step forward, we are sure that the first number is greater than the second number. If A is greater than or equal to B, A modulo B will be less than A half, so we are sure that A will lose at least half of it. So we make sure that we are really making our numbers smaller. So the point is that we want to show that if A is greater than or equal to B, A modulo B is going to be at most A half. It's going to be less than A half. Why is that true? Why does it work? So we have two cases. in order to show this, we have two cases. Either B is greater than or equal to, or let's say B is greater than a half. If B is greater than a half, and we know that B is less than or equal to a, we can say that a modulo B is equal to a minus B. If B is greater than a half, a modulo B will be a minus B, because you can only take out one B from A. You cannot take two B's, because 2 times B is going to be greater than A. So a modulo B is going to be a minus B, and since B is greater than a half, it's going to be less than, and because B is greater than a half, it's going to be less than a minus a half, which is a half. So in this case, a modulo B will be less than a half. If B is greater than a half, a modulo B is going to be less than a half, because a modulo B is going to be a minus B. So this is the first case. The second case is that B is less than a half. So B is either greater than a half or less than or equal to a half. We know that a modulo B is going to be a number from 0 to B minus 1. A modulo B is always a number from 0 to B minus 1. So a modulo B is going to be less than B. And we know that B is at most a half. Therefore, in this case also a modulo B is less than a half. So I showed that I had two cases, I considered two cases. I said that either B is greater than a half or B is less than or equal to a half. If B is greater than a half, a modulo B is going to be a minus B. And since B is greater than a half, it's taking out at least half of A. So a minus B is going to be less than a half. If B is less than or equal to a half, a modulo B is going to be less than B, always. It's going to be from 0 to B minus 1, so it's going to be less than or equal to a half as well. So I showed that in all cases, a modulo B is less than a half, if A is greater than B, greater or equal to B. If B is greater than A modulo B is equal to A. If so we can say that when we're taking mod, if we are taking a modulo B, if B is greater than a modulo B is equal to A, because we cannot take out any B. But if B is less than or equal to a modulo B is going to be less than or equal to a half. So a modulo B either is equal to A or is less than a half. A modulo B always is, let's make it a bit larger. A modulo B is either equal to A for when B is greater than A, or it is less than a half for when B is less than or equal to A. So, is everything clear so far? Are you completely okay with this? If you completely understood it, put a plus or use this emoji. Otherwise, let me know to explain any part again. Nice. This is also a very important fact in number theory. A modulo B, when A is greater than or equal to B, is less than a half. And it will be used in many problems. So this is very important. Okay, so if you're all okay with that, let's move on. So we were talking about GCD. I'm saying that in order to calculate GCD, we can say this. When we want to calculate GCD of A and B, we can say int of GCD int A int B, and we can just say this. We can say that if b was 0, I mean, this is my base case. If b was 0, I want to just continue. I said that at the beginning. I will continue so that for me a and b will be both small enough. So when I make them small enough, then it's going to be easy for me to calculate the GCD. Here, small enough for me is going to be when one of them is 0. The smaller one is 0. And because I want the smaller one to be b, I will continue as long as b will turn into 0. So I say that if b is equal to 0, as I said, GCD of a and b is going to be equal to a. So I will return a if b is equal to 0. Otherwise, I say that GCD of a and b is going to be equal to return GCD of a, b, and a modulo b. And that's all. This way I want to calculate GCD. And the point is that maybe at the beginning a is not greater than or equal to b. I'm trying to assume that the first number is greater than or equal to the second number. Greater than second number, even greater than the second number. At the beginning it doesn't have to be like that. I mean, at the beginning you can call GCD of, for example, 2 and 7. And a is less than b. That's okay. But the point is that if you see here, from the second step forward, always the first number is greater than second number. Because always when you call GCD, the first number is some b, the second number is some number modulo that's b, which is from 0 to b minus 1. So from the second step forward, always the second number is less than the first number. And that's why we only consider the case where b is 0. I mean, even if you give as an input, you give GCD of 0 and 3. The first time it sees that b is not 0 and it will continue even though a is 0. But the point is that next time it will call GCD of b, which is 3, and a modulo b, which is 0. So next time GCD of 3 and 0 will be called, and then b is going to be 0. So don't worry that the first time a is not greater than b, because from the second time forward, I mean, even if a is less than b or a is equal to b, if a is less than b, you can see that easily they will be swapped in the first step. And the point is that from the second step forward, the first number is going to be the greater one. So our base case is when b is going to be equal to 0, and if b is equal to 0, we'll just easily return a, otherwise we return GCD of b and a modulo b. And this way we calculate GCD. So far, do you agree with the correctness of this algorithm? First, we want to make sure that it is correct, and then we're going to see that what is its time complexity. If you are okay with that, please use this emoji or put a pause. Yeah, we will talk about time complexity, yeah. These are very good guesses. Auron, do you know Persian? Your name is Auron? I don't know. You are good in Persian. Yeah. This is a very good guess. We're gonna get to it. Yep. So far we just want to make sure that it is correct. We just said that, I mean, we used the fact that we used that fact number 1 that was saying that GCD of a and b is going to be equal to GCD of b and a modulo b. So they are really equal, and this really gives you the correct answer. Now we want to see that what is the time complexity of it. What is the time complexity? So for the correctness, let's make it even bigger. For the correctness, we used fact number 1. Now, in order to show that the time complexity is also good, I'm going to use fact number 2. In order to show that time complexity is also good, I'm going to use fact number 2, which was saying that a modulo b is less than a half when a is greater than b. The point is that, as I said, maybe the first step a is not greater than b, but from the second step a is always greater than b. And when a is greater than b, each time we are dividing a at least by 2, our number is going to be less than an a half next time. So in each step, we are going to divide one of our numbers by 2, or let's say that one of our numbers loses half of itself. One of our numbers loses half of itself. And the point is that our numbers are up to something. I mean, a is up to something and b is up to something. How many times a can lose half of itself until it becomes 0? A can at most lose half of itself at most O of log of a times. It is a and it's going to become 0. I mean, we want to see that how many times I can divide it by 2 so that it turns into 0. It's going to be O of log of a. So for a, this can only happen log of a times. For b, it can only happen log of b times. So in total, we can show that the answer is going to be at most, I mean the time complexity will be at most log of a plus log of b. Because we know that each time one of our number will lose half of itself. The first number can lose half of itself at most log of a times. The second number will lose one of its half of itself in at most log of b times. So in total, this will take log of a plus log of b. And if a and b are from the same order, it's going to be O of log of a. Is it clear? Does it make sense? If it makes sense, please again use the emoji, this emoji, or put a plus. So basically, I just showed that the first one can lose half of itself log of a times, the second one can lose half of itself log of b times. Thank you very much. So this is how we show that it has a good time complexity. But also, not only this, we can also say that it will be O of log of minimum of a and b as well. This is for the case that a and b have different bounds. For example, assume that a is a small number, but b can be a very large number. In this case, it's important to show that it's going to be O of log of minimum of a and b. And why is that? The point is that numbers will alternate. I mean, first a is the first one, then b is the first one. And the point is that after the second step, I mean, whatever is minimum of a and b, after at most 2 steps, both of them will be less than or equal to that. I mean, whatever is minimum of a and b after at most 2 steps, both of them will be less than or equal to that. So from then, both of them are at most that much, so log of a plus log of b is going to be 2 times log of minimum of a and b. So the point is that we can also say that it's O of log of minimum of a and b, but most of them, a and b are around the same number, so it's going to be O of log of a, for example. So anyway, whatever is the range of your number, it's going to be O of log of that. So now even if a and b are up to 10 to the power of 18, we can calculate the GCD. We can calculate it. Right. So this is how we calculate GCD. Is it clear? We need more of these. Do you mean the topic streams or these things about GCD? So this is how we can calculate the GCD of A and B. Thank you very much. Okay, sure. Yeah, we have weekly topic streams, and we try to talk about all the topics in these topic streams over several weeks. So my plan is that maybe after a year, almost all topics will be discussed. It is planned to be on Fridays, but sometimes it will be changed to Saturday. But weekly, we're gonna have these topic streams. There should be a buzurg level in Sieve. Thank you. So now that we found out how to calculate GCD, we can now try to solve some problems from Codeforces. I mean, I just schedule streams. I mean, if your rating is above some rating, you can schedule streams on Codeforces. Okay, so now let's talk about a problem and let's see how we can solve it. This problem is from Codeforces. Let me send you the link of this problem. It is 1458A. Okay. So it's saying that you are given two positive integer sequences, a1 to an and b1 to bm. For each j from 1 to m, find the greatest common divisor of a1 plus bj to an plus bj. So you have two arrays, a1 to an and b1 to bm. For each j from 1 to m, each time you take one of these b's, for example bj, and add bj to every of these elements, a1, a2 to an. Add bj to each one of these ai's. And we want to say that what is going to be the GCD of these numbers. For each j you have to say this, so your output should have m integers. For example, in here your numbers are 1, 25, 121, 169. First of all, you add 1 to all of them, so it's going to be 2, 26, 122, and 170. The GCD is going to be 2. Then you're going to add 2 to each one of them. It's going to be 3, this is going to be 27, this is going to be 123, this is going to be 171. All of them are divisible by 3. Then you're going to add 7 to all of them. Then you're going to add 23 to all of them. So each time you take one of BJ's and add that BJ to each one of AI's, and you want to see that what is the GCD of all these numbers. What is the greatest common divisor of all these numbers. And let me write the limits in here as well. N and M are up to, as you see it here, N and M are up to 2 times 10 to the 5th. AI's are up to 10 to the 18th, and BI's are up to 10 to the 18th as well. So the problem is clear, right? The screen was not clear. Thank you very much, Mohammed. I mean, it really means a lot. I'm really happy if it is helping you. Thank you. Was the statement clear? Did you completely understand this? Sure, definitely. As I'm saying, we are gonna have it weekly, and I would love to see you on these topic streams each week. I mean, as much as more people are watching this, I'm gonna also have more motivation to make more of this, because I believe that it's really having some great effects. So if you like it, I would really appreciate it if you can like this video, subscribe to this channel. I mean, that helps this stream to be promoted. And also, more importantly, if you know other people who might get benefit from these live streams, let them know about these live streams as well. I think that will help a lot as well. I mean, if I see that more people are watching this, I definitely will be more happy to have more of this. I will have a lot more motivations, and this would also be more effective, and this is very important. Also, if you want, you can join our community in our Telegram channel or our Discord server, which is here. We're gonna have a community, several thousand people are there, and we will have our further discussions in these communities. Thank you very much. Yeah, I would love to see you here every time. I would really love to. And also, if you can let your friends know about it as well and tell them to join too, because I would love to see more people on this live stream as well. So, was the problem statement clear? So each time, as we said, we take one of these bj's and add bj to all of these elements, and we have to say that what is the GCD of these numbers? an plus bj. Increase the thickness of the pen. Yes, I can increase it even further. Maybe this is better. Thank you very much for your suggestion. Yeah, let me know if anything can be changed to make it easier to see or make the stream easier to understand. If there's any issue with the sound, with the whiteboard, anything, let me know. So this is what we want to calculate. Each time add some bj to all the AIs and understand that what is the GCD of all these AIs. It will be same for every bj. This is one suggestion that we have, but the GCD will not be the same for all the bj's, because if you see it here, when you add 1 to all of them, the GCD will be 2. When you add 2 to all of them, the GCD will be 3. When you add 7, the GCD will be 8. When you add 23, the GCD will be 24. So the number will change, but something else can be very similar by subtracting. Yes, that is a very important thing. That is a very good idea. Any other ideas? So what do you think we should do? I mean, we want to calculate GCD of A1 plus BJ, A2 plus BJ. As I said, in GCD we can have more than 2 numbers. To A1, AN plus BJ. Nice, that is great. I hope that you get there. I would love to help you to get there. I hope it can really help you to get there. So we can use one important thing again. If you remember, we said a very important fact. We said that GCD of A and B is equal to GCD of A and A minus B. Maybe let me change to this marker. It would be equal to GCD of A and A minus B. And this is not only true for one number. I mean, it's not only true if we have 2 numbers in our GCD and we just change one of our numbers. It can also be true if we consider that we have several numbers. For example, assume that we have 3 numbers, A, B, and C. Assume that they are in the sorted order. I can say that GCD of A and B and C is equal to GCD of, assuming that A is greater than B greater than C. For example, they are sorted. I can say that GCD of A and B and C is equal to GCD of A and A minus B and A minus C. Because again, if all of these numbers are divisible by d, then a minus b is also divisible by d, a minus c is divisible by d. So again, if you remember that what were the proofs here, you have them in there as well. So these proves that when we in one side we had d, in the other side we have d as well. In here we can say that as well. My voice is low, you can't hear me? So what I'm saying is that GCD of A and B and C is equal to GCD of A and A minus B and A minus C. So therefore, there's one very important thing in here, and that is this: when you increase each number by bj, even though your numbers will change, but their differences will not change. So when you add bj to a1 and you add bj to a2, the difference of these two numbers, a1 plus bj minus a2 plus bj, remains the same. It is still a1 minus a2. So the differences will not change when you add bj to all the numbers. So when you consider a1 plus bj, a2 plus bj, and so on, an plus bj, we can just say that GCD of these numbers at all, GCD of a1 plus bj to an plus bj is going to be equal to GCD of a1 plus bj and a1 minus a2, the absolute value of a1 minus a2. If it was negative, just make it positive. Okay. a1 minus a2, a1 minus a3, and a1 minus an. You can also assume that a1 is the maximum number, so that all these numbers are positive. So the point is that these differences will not change. If you consider these differences, they will always remain the same, whatever your bj is. Adding a constant number will not change anything. So the point is that these parts can be pre-calculated for everything, for every queries, for all the queries. You can first see that what is the GCD of these numbers? What is GCD of a1 minus a2? For example, in here, a1 minus a2 is this is 24. We consider the absolute values. Let me write here. We have 1 and 25. So this is 24, the difference. The difference between 1 and 121 is 120. The difference between 1 and 169 is going to be 168. You can see that what is the GCD of these numbers? GCD of these numbers in this example is 24. So this way, if you do this, oh, I wasn't on my screen. So I was just saying that 1 minus 25 is 24, the difference. The difference of 1 and 121 is 120. The difference between 1 and 169 is 168. The GCD of these numbers is 24. So when you know this GCD, you already know that what is the greatest common divisor of these numbers, and you just need to add only one number, a1 plus bj, to it. And just consider the GCD of, calculate the GCD of this number, whatever it is. For example, it is some d. You just need to calculate GCD of that pre-computed d with a1 plus bj. This is the key idea of this problem. When you're adding constants to all the values, the differences will not change, So let's consider a2 minus a1, a3 minus a1, a4 minus a1, to an minus a1. Let's consider all these numbers, calculate the GCD of all of them, and save it somewhere. When some bj will be added, just calculate a1 GCD of a1 plus bj and this d. And that's going to be your answer. For example, in here, this GCD is 24. First, you have 1, so you only calculate GCD of 1 plus 1, so it's going to be 2 and 24, so it's going to be 2. Then you're adding 2, so you're just going to calculate GCD of 1 plus 2 and 24, it is 3. Then you're adding 7, so you just calculate GCD of 1 plus 7 and 24, it is 8. Then you're adding 23, so you're calculating GCD of 1 plus 23 and 24, so it's going to be 24. And this way, everything will be calculated. So the main idea was that when you add these numbers, the differences will not change. And you calculate the GCD of these differences and save it somewhere. It's going to be D. And each time you just calculate GCD of A1 plus Bj and that D. And that's going to be all. This way the problem will be solved. Okay, is it clear? Hi Colin and hi Sam. When is NAQ? I mean, if it is now, I cannot join. But it's very funny that you're here. No, I'm not gonna do meta IQ. If it is clear, please put a plus or use this 100. And Colin and Sam, I will touch. When this stream will be ended, I will send a message to you, but maybe I cannot. Thanks. Yeah, it's funny that. Yeah, okay, sure. Nice. Yeah, I try to come to Seaways. That's gonna be fun. Okay. So at 2 p.m. I'll try to join you. So, is it clear completely? So, everything that we had to say in this problem was to just calculate these differences and just calculate the GCD of this first number and these differences. So this way everything will be calculated. Shall we move on to the next thing? If you have any questions, let me know. If you are completely okay with that, please either put a plus or use this emoji. What do you mean by trying some AP stuff? Yes, in graph, we will definitely cover more advanced topics as well. So, okay. So now let's move on to the next topic. If it is completely clear, that's what was going on in here. The next topic that is also very important. Now that we have talked about GCD, the next topic is prime numbers. Prime numbers. So, I like to. Well, we can talk about that in the next stream, right now, because this stream is about numbers already. We have to stick to this topic, but we will also talk about these topics as well. I mean, definitely most important thing is that you solve so many problems. That's a general rule for competitive programming. You have to solve so many problems. But we can talk in detail in the next topic streams. So, the next important thing is prime numbers. Assume that, no, I'm not participating in Meta-Hacker Cup. Assume that we want to calculate all the prime numbers from 1 to some n. Okay, n can be anything. For example, n can be up to 10 to the 6. Assume that we want to calculate all the prime numbers from 1 to some n, and n can be up to 10 to the 6. For example, assume that we want to calculate all the prime numbers from 1 to 10 to the 6. How can we do this? And a prime number with high probability you are familiar with prime numbers. A prime number is a number that only divides 1 and itself. So a prime number, p, is a number that only divides 1 and p itself. So how can we do this? Well, the main idea to calculate prime numbers, there are two ways that we can do this. The first thing that comes to mind, again, is to have a function to check if a number is prime. And how does that work? We can just have a for from 1 to n. For example, assume that we have some x and we want to check if x is a prime number. We can just have a for from 1 to x, or from 2 to x minus 1, and if x divides any of those numbers, x is not prime. Otherwise, x is a prime number. So because a prime number must only divide 1 and itself, x must only divide 1 and x. If I have a 4 from 2 to x minus 1 and x divides any of these numbers, x is not a prime. So one idea can be this, and it's going to be in O of x. This way our time complexity will be O of x if we do this. But we can also optimize it a little bit. Do you have any idea to optimize it, make it a bit better? We want to check if x is prime. So we are trying to find all the numbers from prime numbers from 1 to n. One idea is to check each x if it is prime or not, and then we have a for on all the x's. So we have a for on all the x's from 1 to n, and for each x, again, we have an O of x for to see that if it is prime or not. So our time complexity in total is going to be O of n squared. Because we have a for from 1 to n on each x, and then we have a for of O of x to see that if that number is prime or not. And in order to improve it exactly, the idea that we can use is sqrt. Well, the point is that if a number is not prime, for example, if x is not prime, it has it has divisors other than 1 and itself. For example, you can show it as sum a times b, such that both of a and b are greater than 1 and less than x. The point is that when one number other than 1 and x, for one number other than 1 and x, x is divisible by that, there's also, if you have some a, you also have n x minus over a. If you have an a that x divides that, if you have an a that x divides that a, x also divides x over a. For example, we know that 10 is not a prime number. it is divisible by 2, and when it is divisible by 2, it is also divisible by 10 over 2 as well. It is divisible by 5 as well. So I'm saying that the main thing that I'm saying is that you can write x as a times b if x is not prime. So let me write it here. If x is not prime, a prime number, you can write x as a times b such that both a and b are greater than 1 and less than x. A and b can be also equal as well. For example, when you have number 4, a and b are both 2. So they can also be equal. So the point is that when you write x like this as multiple of a and b, one thing that you can say is that at least one of a and b, at least one of them is at most a square root of x. So you can write, because if both of them are greater than a square root, if a is greater than a square root of x and b is greater than a square root of x, then a times b is going to be greater than x, which is a contradiction. So this won't happen. At least one of them is less than or equal to a square root of x. Therefore, if x is not prime, the fact that we get is this: if x is not a prime number, it has a divisor from 2 to a square root of x. This time not to x minus 1. This time our 4 is to a square root of x, not to x minus not to x minus 1, right? Excuse me, I was sick a week ago and still some effect is there and I'm not still completely fine. So if x is not a prime number, it has a divisor from 2 to a square root of x. So our second 4, instead of being from 2 to x minus 1, can be from 2 to a square root of x. This is an optimization that makes it, instead of a square root of x, it makes it O of a square root of x, which is better. So this way we can find out if x is prime or not in O of a square root of x. This is a very good way to find out if some x is prime or not. So we can, in O of a square root of x, we can find out if x is prime or not, and then we have a 4 from 1 to n to check that for each number. So it's like we have sigma for each number from 1 to n of a square root of that's I, and because a square root of I for all of them is less than or equal to O of a square root of n, this is gonna be less than or equal to n times a square root of n times O of a square root of n, which is equal to O of n a square root of n. And the point is that you can show that it's not much less than that as well, because at least half of them for I from n half to n, O of a square root of I is gonna be, I mean, you can also show that sigma of I from 1 to n, O of a square root of I, this is greater than or equal to I from n half to n, O of a square root of I. Because this way you are just considering half, you are just ignoring some i's from 1 to n half. This is greater than or equal to this, and this is greater than or equal to n half times O of a square root of n half, which is also from O of n square root of n. So this is really n square root of n. The order is going to be n square root of n, capital N. So we improved it from n squared to n square root of n. This is better, but it is not still the best possible case. Is it clear so far? If it is, please let me know again in the chat. So if any part of it is not clear, let me know to explain it again. Otherwise, you can put plus or use this emoji to let me know that you're completely okay with it. So we have improved it. So we improved it to O of n square root of n. Mamnoon or Zeb. I don't know how to pronounce your name, so if you can help me with that, that was also helpful. This is better. I mean, this approach is better, but this is not still the best approach. I mean, we still have a better approach for the problem of finding all the prime numbers from 1 to n. But in order to find out that one number, is a prime or not, we can do it in O of a square root of x. That is a good approach. I mean, the point is that we do not need to really do this function for each number individually. We have a better way of finding out all the prime numbers. Your idea, why I from 5i times I less than I plus equal to 6? Why only I plus equal to 6? Orangzip. Thank you, Orangzip. Each multiple of a number is not prime, exactly. We can talk about that as well. The number of elements whose smallest prime factor is I. You can, in an approach similar to DP, you can find out the smallest prime factor of any number. I will talk about it, how to find out the smallest prime factor of each number. And then you can count that how many of them are equal to I. So far we had this idea that helped us to check if a number is prime or not in O of a square root of x. Now I want to make everything better and come up with an idea of finding all the prime numbers from 1 to n. And the idea is this. I mean, the point is that assume that you have figured out that P is a prime number. P is a prime number. Well, it definitely means that 2p, 3p, 4p, and so on are not prime numbers. Not only it is true for prime numbers p, the numbers that are prime, but also for any number, for any p greater than 1, you are sure that 2p, 3p, 4p, 5p, they are not prime anymore. So for any x, we can also say that for any x greater than 1, 2x, 3x, 4x, and so on are not prime numbers. None of them are prime numbers. For any x greater than 1, 2x, 3x, 4x, and so on are not prime at all. So this is very important. So our idea is going to be like this. Let's do this. First, let's do this and show that it is correct. And then again, let's analyze that, what is going to be the time complexity of it. Assume that we have a 4 int I equal to 2, I less than or equal to the input n I plus plus. Assume that we have an array that shows that each number is prime so far or not. Each number is a prime or not. Assume that initially for all numbers we set that they are prime. We just know that prime of 0 and prime of 1 is false. 0 and 1 are not prime numbers. So initially for everything, prime of I is equal to true. We initially set that everything is a prime, then gradually we remove the numbers that are not prime anymore. So initially all the numbers are prime. First we remove 0 and we remove 1. We set prime of 0 equal to false, prime of 1 equal to false. Then we go from 1 to n and we just say that for int of j equal to 2 times I, j less than or equal to n, j plus equal to I, prime of j is equal to false. So what I'm doing in here is this. I'm just going to all the numbers from 2 to n, similar to here, for any x greater than 1. I'm going over all these multiples, 2x, 3x, 4x. So I start from 2 times I, and I go as long as j is less than or equal to n. Each time I add I to it. It's like I'm adding another x to it. So I'm going over all these multiples of I, and I say that prime of j is equal to false. If I do this, first of all, I'm going to show that this is true. I mean, this is a correct algorithm. At the end, for each number that prime of I is equal to true, that number is a prime number. If it is not, if it is equal to false, that prime is not a prime number. So how can we show that? Well, first of all, assume that prime of I is equal to false for some I. Prime of some, let's say x, is equal to false. It means that something have made it false. For some number, we had a 4 and its multiples, and we made prime of I to be false. And we showed that if we make something false, it's really not a prime number. It's really a multiple of some number greater than 1. So when we go over x and we make it false, it definitely is not a prime. Not a prime. So if it is false, it definitely is not a prime. If prime of I, on the other hand, if prime of x is true, it means that nothing have made it false. Nothing have made prime of x to false. So it means that there was no number from 2 to x such that x was a multiple of it. Nothing went over x and made it false. So no number greater than 1 was really a multiple of it, other than x itself. So it really is a prime. Let's say a prime. So in this case, x is really a prime number. So we showed that if prime of x is equal to false, it is not really a prime number. But if prime of x is true, it's really a prime number. Can you explain in Hindi language? I don't know Hindi language. I'm not Indian. So do you agree that it is true? Do you agree that it is correct? We haven't yet talked about what is the time complexity. But we want to first show that it is correct. Do you agree with this? At the end, if prime of x is false, it means that some number from 2 to x minus 1 was a divisor of it. So it's not really a prime. If prime of x is true, it means that none of those numbers were a divisor of x. So it is really true. If you have any questions so far about the correctness of the algorithm, you can let me know. I'm not sure what it is. But for now, guys, Are you completely okay with this? If you have any issues, let me know about it to explain it again. So if prime of x is false, it's not a really prime number. If prime of x is true, it's the number is a prime number. And yeah, sure. I mean, you can comment the name of this problem in this stream, and we can talk about it in the next sessions. No, I'm not doing calculate. Yeah. So this is correct. This is a correct algorithm. Now the question is, what is the time complexity? Let's go over. We're blocked by anywhere. So the question is now, what is the time complexity? Let's take a look at here what we are doing here. We start from I equal to 2 and go I to n, I plus plus. Each time we are adding j by I. So how many times this for will be executed? I mean, we start from 2 times I, but the most important thing is that we are adding I to j each time. And we go to n. Each time we are adding I and we are going to n. So what does it mean? Yes, that's correct. We can also start j from I times I. That is right. Right. So do you agree that this part will be executed n over O of n over I times? Why? Because each time we are adding I to j and it will go to n. So each time, I mean, it's going to be at most n. Each time we're increasing it by I. Each time we're increasing it by I and it will go to n. So it will be increased n over I times. Right? So, and we can just say that it is less than or equal to n. We don't really need to even use O notation here because we know its exact value. I mean, it is at most n. Wait a minute. Okay. It is at most n over I. Precisely. So we start from I equal to 2 and go to I equal to n. So the point is that our time complexity is going to be n over 2 plus n over 3 plus n over 4 to n over n. This is our time complexity. Okay. And let's assume that we have some n over 1 as well. I mean, let's add n over... I mean, let's say that, first of all, this is equal to n times 1/2 plus 1/3 plus 1/4 to 1 over n. So it is equal to n times this. And this is a very important thing. It is a very famous thing. It is called, yes, as you said, you're right about it. It's called harmonic series. And we want to show that it is small. It is not really a lot. So if I show that it is small and it is not a lot, I show that my algorithm is fast. So we have n/2 plus n/3 plus n/4 to n over n is equal to n times 1/2 plus 1/3 plus 1/4 to 1 over n. And we show that this number is we want to show that this number is relatively small. If we show that it is small, we show that our algorithm is fast. Let's say that, so we want to bound, what we want to talk about is this number. We want to bound 1/2 plus 1/3 plus 1/4 to 1n over n. We have a very famous series in mathematics named Harmonic Series. We show it with h of n. This is less than or equal to h of n because the definition of h of n is this. h of n is 1 over 1 plus 1 over 2 to 1 over n. So it is completely the same thing, but it starts from 1. I mean, nothing will change. Let's just add 1 to it. Add 1 over 1 to it as well. I mean, just assume that we add 1 over 1 as well. It just becomes a bit greater. It becomes a bit larger. I want to show that this h of n, so this is around h of n. I want to show that this h of n is a small number. I want to show that h of n is a small number. Well, in fact, I want to show that h of n is from theta of n, is from theta of log n. If I show that h of n is from theta of log n, this shows that in general what I have in here is around log n, a constant times log n. And theta means that it is both from O of log n and omega of log n. In other words, it's saying that h of n is from O of log n and it is not really less than that. So what I'm saying is that h of n is from O of log n and it is not really better than that. It is really log n, around log n. How do I show that? Well, h of n is going to be equal to 1 over 1 plus 1 over 2 to 1 over n. Well, the point is that I can group these numbers. I can say that one group is 1 over 1. One group is 1 over 2 plus 1 over 3. One group is 1 over 1 over 4 and 1 over 5, 1 over 6 and 1 over 7. One group is from 1 over 8 to 1 over 15 and so on. Well, the point is that for each group, for example, for this group, I can say that this is less than or equal to, I mean, in each group, you can easily see that their first number is the greatest one among them. In each group, the first number is the greatest number among them. For example, this is really, we have 8 numbers in here, and each one of them, the greatest one of them is 1 over 8. So this number is really less than or equal to 8 times 1 over 8. Because 1 over 9 is less than or equal to 1, is less than 1 over 8. 1 over 10 is less than 1 over 8. 1 over 15 is less than 1 over 8. So we have 8 numbers, each one of them are less than or equal to 1 over 8. So the whole thing is less than or equal to 8 times 1 over 8, which is 1. In here we have 4 numbers, each one of them less than or equal to 1 over 4, which is 1. In here we have 2 numbers, each one of them less than or equal to 1 over 2. Sorry, not equal, less than equal. So it is 1. In here we have 1 number, each one less than or equal to 1 over 1, which is 1. So you see that the sum of each group is at most 1. And how many groups do we have? How many groups do we have? We know that we go to 1 over n. The last number is 1 over n. So how many groups do we have? So the first group started from 1 over 1. The second group started from 1 over 2. The third group started from 1 over 4. The next one from 1 over 8, and so on. Exactly, it's going to be log, because if you see, the start of each group is 1 over some 2 to the power of k, and it goes to 1 over 2 to the power of k plus 1 minus 1, so that the next group again starts from 1 to the power of 1 over 2 to the power of k plus 1, and so on. So the point is that the start is the power of 2, I mean, in the first numbers, always the denominator has a power of 2. So how many powers of 2 we have less than n? It's going to be log of n. So the number of groups, and when we reach 1 over n, we stop. We do not continue. When we reach 1 over n, we will stop. So the number of groups is gonna be the number of groups is O of log n. It is exactly log n. I mean, it is at most log n plus equal minus 1, for example. So it is around log n itself. Each group has sum at most 1. So the sum, the total sum is O of log n. You have log n groups. The sum of each one is at most 1. So in total, the sum is log n, O of log n. So I just showed that h of n is from O of log n. H of n is less than or equal to some constant number times log n. Right? Is it completely clear? If it is clear, again, please put this emoji or put a plus. So 1 times 1 minus half over n. I didn't completely understand what you mean. So, is it completely clear? Okay. Okay, so basically what we're saying is we showed that h of n is at most some constant times log n. But as I said, I can also show that it is not way more than log n. In here, we just had less than or equal to. So we know that it's less than or equal to something times log n. But why not? Maybe it is a constant number. Maybe it is even better than log n. I mean, we want to also show that why it is not better than log n as well. I'm just saying that I just say it very quickly that it is not better than log n as well, because you can also group them like this. I want to show that it is really around log n. It's not, it is. We showed that h of n, we show that it is less than n log, is less than, log n. We showed that because we have at most log n groups. I mean, the number of groups is exactly at most log n. It's not even O of log n. It is at most log n, and each one of them has some at most 1. So h of n is really at most log n. But I want to also show that h of n is greater or equal to log n half. Why is it so? Guys, take care of all this. I mean, focus on all of these things, because these are really important in number theory. You need to comprehend all of this to have a good grasp of number theory. So why it is at least log n half as well? Because you could also group them like this. You could also say that, I mean, your groups can be this. One of them is 1 over 1. One of them is 1 over 2. One of them is 1 over 3 plus 1 over 4. One of them is 1 over 5 to 1 over 8. So this time, as you see, the last number is the power of 2. 1 over 9 to 1 over 16, and so on. And the point is that you can easily show that in each group, for example, in here, you have 4 numbers. Each of them are at least 1 over 8. The last number is 1 over 8. So this is at least 1 half. In here, you have 8 numbers, each one at least 1 over 16. So it is 1 over half. At least 1 over half. This is, in here you have 2 numbers, each one at least 1 over 4. So it is at least 1 over half. And these 2 are also 1 over half, at least 1 over half as well. So again, this time you have log n groups. Each at least 1 half. So that shows that the sum of these numbers is at least log n half. So h of n is really between log n and log n half. This is harmonic series. Harmonic series are very important. For example, you saw that when we want to calculate prime numbers, see that what are the prime numbers, that really helps us. So harmonic numbers, this is harmonic series. The definition of its h of n is that it is 1 over 1 plus 1 over 2, 1 over n. And we show that for this harmonic series, we showed that h of n is at most log n, and it is at least log n half. So h of n, in this situation, we say that it is from theta of n log n. It means not only it's from O of n log n, but it is not less than n log n. It not only is from, why I said n log n, sorry. It's from theta of log n. I'm sorry for my mistakes. It's from theta of log n. So it means that not only is from O of log n, but it is not way less than that as well. Or in other words, also from omega of log n. It is, I mean, this part is saying that h of n is from O of log n. This part is saying that h of a is from omega of log n. So this is how we can just show that this would work, and it is really from theta of log n. So now that we know this, let's get back to our algorithm that we had in here. We had an algorithm to find prime numbers that led us to harmonic series. Now we know that this number is at most h of n. I mean, if you add only 1 to it, it would be h of n. So this is from O of n log n. So we found all the prime numbers. All the prime numbers from 1 to n in O of n log n. We found all the prime numbers from 1 to n in O of n log n. The only thing that we did, we had a for I from 2 to n, I plus plus. In our second for, we were increasing our number by I each time. And this way we found all the prime numbers, and our order to do that was n log n. Because these parts will be executed n over j times, and this way you have n over 2 plus n over 3 plus n over 4 and so on. And this sum is n times harmonic number of n, which is from O of log n. So this way it would work. I guess the concept I can take here is there are nested for loops exist that can run in O of n log n, which is exactly. We have nested loops that we showed that in total they will take n log n steps. Exactly. Yes, exactly. The point sorry. The point is that if we skip all the i's that are not prime, that would also work. So if I is not a prime number, we can also skip it and go to the next number. And you can also start j from I times I. Why this would also work? Because for any number, you want to just find one number that divides it. One number, I mean, you show that a number is not a prime if you just find one number that this number divides that number, right? And the point is that there always exists a prime number. And that prime number is less than a square root of this number that divides that number if number is not prime. So if n is not a prime number, there exists some x such that x is less than or equal to a square root of n, and x is prime and n divides x. This always exists. So this generally means that you can just have a 4 on all the prime numbers in here. So you do it only for i's which are prime. And for them you start from I times I, not 2 times I. Because you want to just go to some j's such that I is less than a square root of j. So you start from I times I. So what I'm saying is that even if the number was not prime, you would skip in here. Even in case that the prime, if the number was not a prime number, you would skip. So you only go over i's that are prime. You say that if I was not prime, you would continue. And you would start from I times I. This would also work. But the point is that because already the time complexity is n log n and it is good enough, you don't really need to do that. But I'm saying that, yeah, that would also work if you would just doing it for prime numbers. And you were just going to multiples that is starting from I times I. Yeah. And guys, sorry for my sound that it changed. I mean, still the effect of being sick is in me. Sorry for this. Okay. So this shows that we found the prime numbers in n log n. Now the question, now is the time to solve a problem with it and see that how it really can be effective in a Codeforces problem. So let's go over a problem, and you ask that what is gonna be the next session's topic. We will continue number theory because there is still a lot that we have to talk about number theory. So let's solve a problem from Codeforces. Before that, let me get back here in a moment. I will be back here in just a minute, sorry. Okay guys, sorry for that. I hope you can hear me well now. Okay. About the I times I squared optimization that you're asking, well, about it, I'm just saying that you can start from I times I instead of starting from 2 times I, because I mean, I'm saying that if you start from I times I, you are going over all the j's such that I is less than or equal to a square root of j. So this way you will go over all the j's that I is less than or equal to a square root of j. And because we know that a divisor less than or equal to a square root also exists, that would also work. So if you start from I times I, you will only go over j's such that I is less than or equal to a square root of j. And because we know that for each j, if it is not prime, there must be a divisor less than a square root of j as well, that would also work and there wouldn't be any issue. but it doesn't really change your time complexity much, because it is already good, so you don't really need to use these optimizations really. Okay, where to practice DP and graph tree problems? Well, let me send to you the topic streams that we've already had. We had a lot of trainings in the previous topic streams that I'm sure that it can help you a lot, and we will continue doing this as well. I mean, we will continue to have these topic streams as well. In here, you can watch all the previous topic streams. I believe that can really help you a lot to get better in all these topics. So I really recommend you to watch all of those topic streams, and I hope that will really help you. Hi. So let's solve the CF problem, as I said, and see that how these things can help us to solve problems in Codeforces. So this problem, T primes, let me send you the link in the chat. Sure, I will upload the other vlogs as well. So it says that we know that prime numbers are positive integers that have exactly two distinct positive divisors. Similarly, so we know that what is a prime number? They have exactly two distinct positive integer divisors, 1 and themselves. Similarly, we call a positive integer t prime if t has exactly three distinct positive integers. So t prime is an integer that has exactly three positive integers. You are given an array of n positive integers. For each one of them, determine whether it is t prime or not. So, first of all, what does it mean to be a t prime? What does it mean to have exactly three distinct positive divisors? What do you think a number should be so that it has exactly three distinct positive divisors? What do you think it can be? How a number can have three? Exactly, it must be a square of a prime. Exactly. So if a number is gonna have three divisors, it means that definitely this x must be divisor by 1. I mean, it definitely is a multiple of 1, and it is a multiple of x, and it must be only one other number that is a divisor of x. Assume that it is a. Well, we showed that if x is divisible by a must be multiplied by something that will be equal to x. So a must be multiplied by x minus x over a such that it would be x. We know that x over a is not 1 and it's not x, because a is greater than 1 and is less than x. So this one is also greater than 1 and less than x. So this must be equal to a itself, because we don't have more than three divisors. So x over a is also a divisor of x. It's not equal to 1 and it's not equal to x. So it must be equal to the third one, the other divisor. So it must be equal to a. So x over a must be equal to a, and x is equal to a squared. And a itself must not have any divisors, because if a is also divisible by some b between 1 and a, then x is divisible by that as well. So a must be prime. B prime. The point is that if x has three divisors, x is a prime number to the power of 2. X is some p squared. Okay, so if x has three divisors, x is some p squared. So we want to find that for each of these numbers, we want to find that if they are some p squared or not. For example, 4 is a prime number to the power of 2, so it's yes. 5 is not a prime number to the power of 2, so it's no. 6 is not a prime number to the power of 2, so it's no. So the only question is that, I mean, when we get an x, so we can say that for each query, while q minus minus, each time while q minus minus, each time we get some x as input, we get some x, and we want to see that, let's say y is equal to sqrt of x. And you can use the built-in sqrt function. In here, because x can be a long line, you have to use sqrt_l function. So you add an L at the end of sqrt, which shows that this number is a long line. Y is sqrt_l of x, and you just need to check that if y was prime and y times y was equal to x, y times y is equal to x, you can say that the answer is yes, see out yes. So it means that x is y squared exactly, because when you have, this is some ints, you are casting sqrt_l of x to some ints, so you're rounding it. Maybe y times y is not exactly x, it's around x. So if it was exactly x, so it means that x is equal to y squared, and y was a prime number, you have to see out yes, else you have to see out no. And that's going to be all about this problem. So you just need to first find out if that number is prime or not. We talked about how to find out if a number is prime. We talked about how to find out if a number is prime or not, using that solution that we had in here. That I have to still talk a little bit more about it. I haven't yet told you that's what is its name. This way we can find out if a number is prime or not, and then each time when we get a number y, then it's gonna be if sqrt of x is y, we just need to check if y times y is equal to x and y is prime. If that was the case, this number is really a prime number to the power of 2. Otherwise it's not, and the answer is no. How are you able to say it's the square of prime so quickly? As I said, we just use the sqrt function. This gives you approximately the square root of x. Maybe the square root of x is not really an integer. Maybe it's a decimal number. But the point is, you're casting it to an integer. It means that what is a square root of x is around x, is around y. If it was really y, if y times y is exactly x, if y times y is exactly x, and y was a prime number, x is y squared where y is prime. So the answer is going to be yes. Otherwise, the answer is going to be no. So let's get back to our solution to find out if a number is prime or not. And let's answer one of your questions that you asked on how to find the smallest prime divisor of a number. This was how we were calculating. It's weird that I cannot go right. I less than or equal to n, I plus plus. Our solution was like this. We had another for int j equal to 2 times I, j less than n, j plus equal to I. We just say that in here, we just say that prime of j is equal to false because it has a divisor. Well, first of all, what is the name of this algorithm? What is the name of this algorithm? Can you say that? Are you familiar with the name of this? This is a very famous algorithm to find the prime numbers from 1 to n. Yes, exactly. Sieve of Eratosthenes. Exactly. This is called, I want to make sure that I do not misspell the name, so I write it from here. Sieve of Eratosthenes. Its name is Sieve of Eratosthenes. You have a 4, and in your second 4 you go over multiples of the first number, and you make that number, you say that that prime number, that is not a prime number. This is a very famous algorithm. This is a very famous algorithm to find prime numbers. And not only this, but also it can solve something similar to it as well. For example, you ask the question that how we can find the smallest prime number that divides each number. But the point is, you can easily do that with this as well. You can just define something as smallest prime. You want to find the smallest prime that divides each number. Initially, you set it equal to -1 for everything. So far, there is no prime number that divides this number. You want to find the smallest prime number that divides any number. For each I, you've initially set it to equal to -1. Then you go like this. You have 4 int I equal to 1 equal to 2, because 1 will be removed, because 1 is not a prime number, definitely. You always start from 2, because even if a number is a multiple of 1, it doesn't mean anything. All the numbers are multiples of 1. So you start from 2 and go over the multiples of them. You start from 2, you go to n, and you just say that you have another 4 int j. This time you start from I itself, j less than or equal to n, j plus equal to I. You just say that if smallest prime of j was equal to -1, it means that so far I haven't found any number that j is a multiple of it. So far I haven't found any number that j is a multiple of it. So I is the first number that divides j. I is the first number that divides j. So definitely I is a prime number itself as well when this happens. Because otherwise, if I itself had some divisors, j would divide them as well. But j hasn't divided anything so far. So I can easily say that the smallest prime factor of j in this case is equal to I. So you can see that how sieve, this is still sieve, but you can see that it can also solve some sort of more challenging problems as well. You can use it to find the smallest prime factor of a number. You have a 4i from 2 to n, and you have a j from I to n. And if the smallest prime of j was -1 still, it means that it is not set. It has not found anything that j divides. We haven't found anything so far. If that happens, we can say that the smallest prime is definitely I itself. And that's going to be all about this problem. I mean, this way Sieve can be easily find the smallest prime factor of each j. Does it make sense? If you are completely okay with that, please put a plus or use this emoji. And if it is not, let me know to explain it again. Yeah, sure. Sure, I will explain it again. So I'm saying that if I want to find the smallest prime factor of each number. Initially, I set all of them to -1, which means that they do not have any prime factors so far. Then I have a 4 from 2 to n. I go forward, I start j from I to n and increase j by I. I know that I divides j. J divides I. So j is divisible by I. If the smallest prime of j is equal to -1, it means that j hasn't found anything so far that it is divisible by that. In that case, we are sure that I is prime. Why? Because I is not prime. If I divide some other p, then j would divide p that as well. So the smallest prime of j was not -1 in that case. So I is prime, and I is the smallest prime that divides j, because we haven't yet found any other prime that j divides it, right? So j is divisible by I, and sorry about it. And I is the smallest prime number that j divides it, because before this we haven't found any other number that j divides that. So j divides I, and I is the smallest number that j divides that. So definitely I is the smallest factor of j, and when it is the smallest factor of j, it is also the smallest prime factor of j, because if it was not prime, then it has a divisor that would also divide j. So we can easily say that I is the first divisor of j that we found so far. So it's the smallest prime factor of j. So we can use it to find the smallest prime factor of each number. Yes, we do not even need to check if I is prime itself. We could do that, but we do not even need that, because if the smallest prime factor of j is -1 right now, it means that I is prime. Otherwise, j was divisible by the divisors of I. So we do not even need to check that if I is prime itself. We do not need to. But we are sure that it is prime. In here, we are sure that if we get to here, we are sure that I is prime. Is it clear? If it is clear, please again put a plus or use this emoji. Okay, nice. Nice, very good. Okay. I really hope that you have enjoyed this topic stream. I hope that you learned something about it. This topic stream had some issues of coordination. Time changed. I'm really sorry about that. I hope that I made it up with the content, that you really got help from it. I totally recommend to you to watch the other topic streams as well. You can find them in here. And if you want to support my work, you can like this video, subscribe to this channel, and most importantly, let others know about this topic streams. Invite them to also come to the next topic streams. I would be really happy to see you guys in my topic streams. I hope that I will see you all in the next topic streams as well, and if you can also let others know about it so that they can join as well, that would be also really great. Okay, we will talk more about the time of the topic streams in the Telegram channel. I invite you, feel free if you want to join our Telegram channel in here. In there we talk about the timing of the topic stream. About some tips for reaching specialists, if you want, I can make some video about that. I will put a vote on Telegram as well. If you want, I can make a video about that as well. I have some guideline videos on newbies getting out of newbie, but if you want, I can also make to get reach to a specialist as well. Thank you very much, Kinana. Sure, definitely. Guys, thank you a lot for joining this topic stream. That really means a lot. I hope to see you again in the next topic streams as well. And if you could invite your friends to the topic stream as well, anyone that you think that it would be helpful for them, if it really can help them, if it really can help some people, share the video, share this live stream with them, and let them know about this as well. Thank you a lot for joining. Hope to see you again in the next topic streams. Goodbye for now.